In this segment, we're going to take a look at electricity and combined heat and power generation as uses for landfill gas and biogas. Now, with the last segment on direct combustion, it was important that we were close to a user of that heat or to a system like a district energy system that could use that heat. Electricity is unique from heat in that it's much easier to transmit long distances, and pretty much everyone in Canada is connected to the electricity grid. Electrification is probably the most important energy systems innovation that's going to happen to help us get to a sustainable energy system, and waste can contribute to that. There's some cases where we don't necessarily want to be producing electricity, and that's actually the case in Ontario, which we'll get into, but in a lot of cases, this is a really good way to effectively use landfill gas or biogas and distribute it on a system that already exists, so taking advantage of that infrastructure we already have. Now, there's all sorts of devices that can be used to generate electricity. One of the most common ones that's used for landfill gas and biogas is using a reciprocating engine. So reciprocating means going back and forth. This is the type of engine that's just like the engine you'd have in your car if you have a gasoline-powered car. It's just powered by landfill gas or biogas. And these are pretty efficient machines, about 45% efficient, which doesn't sound like a lot, but it's where we've got to over time. There's some inherent inefficiencies with mechanical engines. But on the upside is if you also collect the heat, you can get up to 95% efficiency. So 45 for the electricity and then 50 for the heat. So if you combine the electricity with the heat, and you're able to use both of them, then you can get a higher overall efficiency. And this strategy is combined heat and power generation, also called cogeneration. If you're looking for a little bit more heat to electricity in your mix, maybe you're operating like an anaerobic digester that is operating in thermophilic mode or something, you could use a micro turbine. So instead of using pistons, like the reciprocating engine, a micro turbine uses spinning turbine blades, which are powered by hot exhaust from the burning landfill gas or biogas. And microturbines have a lower electrical efficiency, but they produce more heat. So overall, you can get a similar efficiency. It's just the percent mix that's different. So based on what you're powering with your system, you might choose a different one. If you're not able to do a combined heat and power generation, then obviously you'll use a reciprocating engine because it's more efficient on the electrical efficiency. So Waterloo landfill example, they don't have a heat user nearby, they just generate the electricity, so they use reciprocating engines. And we've gone on field trips there in the past. We won't be able to go this year, but I'll share some videos when we get to our landfills unit. Now, just for comparison, if we were only to use heat, so the direct use applications we looked at in the last segment, we'd similarly be able to get up to an 85 to 95% efficiency overall, but we wouldn't have any electricity. So there's kind of this gradient across direct heat to microturbine to reciprocating engine in terms of heat utilization going down, electricity going up, and at the very far side we have fuel cells. Now these are pretty early market for waste applications. There are a few companies marketing specifically fuel cells that are suitable to biogas and landfill gas. They claim electrical efficiencies up to 65%. So that's a big step up from the reciprocating engines, and they inherently are more efficient than mechanical engines. So we'll see if fuel cells are taken up more by the market in the future as an innovation on top of reciprocating engines. Now, where our direct heating applications only need to remove moisture, particulates, and potentially siloxanes, for these engines, we definitely want to remove all those things. We also want to remove sulfides, which produce acids which may corrode our metals. So there's a little bit more treatment involved in treating our biogas or landfill gas for use in one of these appliances. Here's a case study of in Leamington, Ontario, which is down near Windsor. Now in the top of the picture, you can see a couple digesters, and there's a structure in front would be the receiving area. So they take in food waste and other organic waste, digest it, and they do combined heat and power generation. So the electricity they can export onto the grid, and then the heat, you can see all these greenhouses in front. So they're able to use both the heat portion and the electricity portion, and that gives them a really high utilization of the energy in that biogas they're generating from the SSO. Now we talked about moisture and particulate removal in the previous segment. So the piece we're adding on, and siloxanes as well, the piece we're adding on is sulfide removal. So depending on the material, you may produce a lot of sulfides and you may not. So you might not need this. If you do have sulfides in your gas, it's going to produce acids, which will be corrosive to the metals in your system. In landfills, drywall is a big culprit for sulfides because drywall is calcium sulfate, and in that anaerobic environment, that sulfate will turn into sulfides. So landfills these days are really trying to control drywall landfilling and keep it out of the landfill to keep this H2S out. In addition to causing problems for the engines, it also is a big source of odor, which is a big thing that landfills want to avoid. Now, to remove hydrogen sulfide, there's similar approaches to siloxane. So you want to adsorb or absorb it with a solid or a liquid that you can either regenerate or throw out afterward. Carbon is a really good adsorbent for sulfide. For absorption, you can either oxidize it, so turn that sulfide into a sulfate, which doesn't have the odor and is soluble, or you can reduce it and turn it into a solid like iron sulfide. So if you contact hydrogen sulfide with iron oxide, it'll actually do a displacement reaction and produce iron sulfide, which is in the solid state, and then it will be out of the gas stream. Now, I mentioned that you might not want to produce electricity everywhere you could with landfill gas. And that's because depending on the electricity grid you're in, there might be better uses in terms of displacing fossil fuel for your landfill gas or biogas. So in this map, it shows the electricity emission factor across Canada. So the emission factor is how much carbon emissions per unit of electricity are generated. So if you have a lot of renewable electricity, the number is going to be small. If you have a lot of fossil fuel electricity, the number is going to be really high. So for example, if you look at Quebec, this is the cleanest electricity in Canada. They have a lot of hydropower in Quebec, which means their emission factor is really low. So we're showing 1.2 grams per kilowatt hours. In contrast, if we look at Alberta, they have 790 grams per kilowatt hour of electricity. And that's because Alberta still uses a lot of coal in their system, which is the worst fuel you can use for almost anything. Ontario's kind of in the middle, so we do have a lot of hydropower, we have a lot of nuclear, we have more and more wind and solar, but we still use natural gas a lot. We got rid of our coal plants in 2014, which was really good for our emission factor. But since we have so much population, when we peak in the summer and everyone's got their air conditioners on, then we switch to natural gas. So we're pretty low on a large scale, but we've got a way to go. But if you compare what we can achieve with using landfill gas or biogas for electricity versus natural gas, I've done some math in the margin. So electricity at 40 grams per kilowatt hour, and it's actually a little bit lower now. This figure is a little bit old, but that equals to 11 grams per gigajoule of energy. And if you look at the natural gas emission factor, that's about 74 grams of carbon for a gigajoule of energy. So if we have 1 unit of energy in our landfill gas or biogas, it's going to be much more effective to spend it as natural gas versus to spend it as electricity in terms of carbon savings. The other thing is, if you remember our efficiencies of our different appliances, 1 unit of gas going through an engine is going to lose more than half of its energy in its transformation to electricity, whereas being used as heat, almost all of it is going to make it through the system. So combined that efficiency factor with the grid factor for the electricity, from a carbon perspective, in a low carbon grid, it will be more effective to use landfill gas or biogas as a natural gas replacement than as a replacement for grid electricity. In somewhere like Alberta or Saskatchewan, definitely it would be better to use it for electricity because it's more efficient than using coal, which is their current source. But that's something to keep in mind, is kind of the overall efficiency with respect to carbon based on where you are in the world. A few more considerations for electricity systems. So we looked at how electricity fits into that big energy system in the first video for this chapter. Electricity, there's a lot of pieces you might think about if you're doing a biogas or landfill gas energy system. So storage, you might not want to spend your electricity as soon as you can. You might want to use it to align with the peaks in consumption. You might want to use it to complement the troughs of production by other renewable power like solar and wind. So you might want to be able to store either your gas or your electricity in battery or pumped hydro or something like that, and use it when it's most effective to use, so to lower the grid emission factor. You need to think about where your project is located, you actually physically be able to connect to the electricity grid. So you need to make sure that that infrastructure can actually carry the energy that you want to put onto it. If you're a landfill located out in the country so that you're not creating odors for people, you might not have strong enough infrastructure in your area, and you might need to think about that grid interconnection a little bit differently, and maybe electricity is not feasible for you. Microgrid integration might be something you think about. So a microgrid, and this is shown in the picture on the right, is a network of electricity generators, users, storage devices that can be operated in a self-contained system called an island, or connected to the larger grid. So you might be part of a microgrid for different reasons of lowering your net power usage or increasing reliability for everyone on your microgrid. You can think about net metering. So net metering means not necessarily sending all your power to the grid. Maybe you're using some of your power behind the meter, and it's just that net amount that's taken from or put on the grid that's accounted for. And you might do that for different economic or electricity emission factor reasons. And then lastly, you might think about what kind of premiums are available for renewable electricity. So in Ontario, there used to be a system called the feed-in tariff system, where you could get a subsidized rate for producing renewable electricity, and that's when a lot of these landfill gas, biogas to electricity systems came online. Now our grid is pretty clean, as you saw on the map. That subsidy no longer exists, but there are other programs where you might be able to get some increased revenue for your electricity being renewable. So that might be something else that steers your landfill gas or biogas project.